So we are going to look at some solutions. We have maze, which we'll try to attempt. We try to attempt solving through maybe Dijkstra. Some tried with even A star, which we haven't learned yet, but it's a commendable effort.
That's why it doesn't work.
Yeah, but you could again maybe we have some brute force, something brutish as well might work, because we have what's our search space? It's 20 by 20. We have a lot of lava or a lot of walls, right? And so it shouldn't be too bad. But there's one issue, interesting issue actually. If you think about it, is this representation, right? When you're looking at the problem, right? How do we represent this as a graph? If you want to solve it as a graph, right? Most likely, right? And actually, what does this 1 and 6 represent? It's technically it's an edge cost, right? It's a weight, right? So, but it seems like it's very tempting to put vertices here, right? And the question is it going to make a difference if you put is this a vertex, right? And you have edge 6 from S to somewhere here, right? So that's a good question. Or do you do a little trick? Maybe you put vertices between, right? Pretend there are nodes between, right? That would be maybe a little bit more correct, but it shouldn't make a difference. We'll see. We'll see. The representation might make a difference. So we have one submission, or 2 submissions. Who has another submission?
Well, I submitted my code, but
It's okay. Maybe we'll leave it for next Tuesday. So let's take a look. Very good, Edwards. Right, maze, and I'll open up the code space. And also need the maze as well. Now where's my code space? I need, of course, also GitHub. Yeah. Now let's look at what? I can't remember my password. All right. Come on. Spam even here. Jeez, there's some people who looks like there's spam even on GitHub. Certainly looks like. Okay, so we are not AI. That's a different course. There's my that's next semester, or and you guys have AI course next year or next semester? Okay, so you will see me again. All right. Now. So algorithms, right, and I'll start the code space. Yeah, this is the correct one, okay. So yeah, of course, first task is reading correctly the file, just to actually get your feet in the door, basically, right? So finding the S and G, and of course things like that. Okay, so exercises, this will be a maze. Do I have it here from before? No, I don't have it, so let's do it here, maze. Oh, come on. What's happening? This cap lock. I'll start the file. I'll just call it maze or something. I'm bored, right? Right. No, actually, I'll do IPython. No, I'll do a notebook. Actually, I'll do a notebook. It's easier. So I just code. Then afterwards, I'll show maze IPython. Yeah, because I can add some documentation and also some instructions here. Right. Select kernel. Select kernel. All right. Let's look at here. We need, of course, some code. Where is the code? Code was here. Downloads. Okay, and of course we need this file, right? We need the file. Again. Now, okay, let's take a look what's happening here. So, we have a file path, we have a list structure, we're going to read the rows, and we're going to strip the new line characters, right? And let's see, yeah, all right, and then we'll have the items, right? So it will be what?
A list of lists.
List of lists, okay, that works. And
Then I create
the graph, start and end. Okay, you know you have directions. Okay, awesome. This looks good. I mean, of course, assuming build graph works, right?
Yeah.
And if, then
You can check it. It will print out the structure.
okay, it prints start graph. It prints everything. Okay, let's run it, right? It checks X. It checks special cases S and G, right? Figures out where it is, right? And it checks directions. It certainly looks decent. For now, let's run it. Let's run it here.
And this version that I submitted is without like the weights, but for
Yeah.
the weights I would just extend the tuple.
Okay, so you created the default dictionary. Okay, so that's
That's the
start and end. Okay, yeah. So of course, so one of the three ways of doing it is basically use how to store it. You can use a dictionary, or in this case, default dictionary, right? And of course now it looks like it's looping, right?
Yeah.
It's going to keep looping. Okay, we'll stop. We'll stop early. So and then you have here you have potential moves. Is that that's?
Yeah, I mean it's like from 1-1 to which vertices can you get?
Okay, and of course then you need the weights, and so you're just trying to find the pass, right?
This was without the weights, yes.
Yeah, so it's all assuming weight is 1 basically, right?
Yeah.
So you just want to try to any pass, anything would do, right? No matter the cost, right? Again, you could do some sort of flood algorithm, by the way, which is actually keep flooding, basically keep going, right? So in this case, probably, well, depth first would probably be faster, right? So let's explore different solutions, approaches right here. If you check about this visualization, right? This one here, right? Right, I'll put here, right? I think this had it has depth first search, right? So depth first search probably, let's see. That first search in this case, well, it went to the as deep as it just didn't make a right choice, right? You can see that first did not quite work well. It's unweighted and does not guarantee the shortest path. You just find any solution, right? You can see how depth first, right? It will gonna find it. Okay, it's a solution, right? Not a very good one. It's a horrible solution, right? Right? Because why? There was no heuristics. There's no. It just kept looking for unexplored place, and as soon, right? So maybe went a really long way around, right? In this case, we basically had a, this maze is out no wall. The only walls were outside. There were no restrictions, basically, right? So you can see how depth first is not so good, right? And because it just did not have a sort of saying didn't have a distinction where to go next, basically, right? So pretty bad, right? I'll stop this actually, right? So let's do breath first, right? Come on. Okay, I need to stop. No, stop. Can you stop this actually? I'll just restart. Yeah, the JavaScript. Okay. So you can see how that first is kind of dangerous. So let's do breath first search, right? Okay, come on. All right. So here, if you go breath first, right? So what's going to happen? It will keep looking, expanding the search space by one level, right? Let's take a look, right? And it does guarantee the shortest path. Why? Because of course eventually, right, it'll keep exploring. If it finds the shortest path, right, it will be, from the closest area. So it's close to Dijkstra actually here in this case, right? So again, you see the search space, right, kept expanding, and then it finds it, right? I'll maybe move it here. Maybe I'll move it again. Skip. I'll move it maybe a little bit here. And maybe I'll add the wall. Let's add some bombs. No, let's add some walls. Come on. What's my JavaScript's not? Come on. Oh, okay. Okay. Something like this. Okay. So let's try the breadth first, right? So what's going to happen? Right? Yeah. So it finds it, right? Now if I do Dijkstra, let's compare this with Dijkstra. Very similar, right? In fact, this little slightly, I think Dijkstra is slightly longer here than actually breadth first because of course the cost is 1, right? The big difference, of course, here for Dijkstra, if all the weights are same cost, right? Dijkstra might not be needed, basically, right? It's basically you have breadth first, basically, right? But let's look at some other ones, right? Swarm algorithms, right? So again, let's look at A star, which is for next Tuesday, right? But let's take a look how it would work here, right? Pretty nice, right? Awesome, yeah. So again, so why does A star work?
Because
So,
it makes the heuristic.
Yes.
And
Yes.
it knows the endpoint. Okay.
yes. So basically, in this case, the heuristic is very simple because we have a two-dimensional space, we have a cheat sheet, we have a formula for calculating, like, right? We need to have optimistic, right? Meaning, or heuristic. We know where we should be looking. We don't want to go there, basically, right, to the left. We want to go to the right, right? So it knows where it should be looking first. There's a preference. So like a costs, when we're doing your Dijkstra, we have an extra cost, right? So it's really cool. Okay, so what else do we have? Look here.
Can you leave it on A star and just make full like,
Wall?
wall?
E-
except
okay,
like
yeah.
one at the top.
Yeah, let's do that. Very good. I think I can do this. Come on, I thought I could do it. Can I do this? No, I guess there's no shift collect. I guess I have to do it by one. Ah, come on, this is evil. I guess, come on, this is ridiculous. I thought I could, I don't know why this is.
Maybe it will be faster. I think. Just taking this one.
Oh, now it works. I don't know what's up with this mouse.
Try this touch screen on the board.
Yeah, maybe touchscreen would be better. Okay, but we got the, okay. Now, let's take a look at the A star, right? Or we can try the different, let's try Dijkstra now, right? Let's try Dijkstra first. So it will expand here hugely, right? Let's take a look. Right? Oh yeah. And now, it's going to probably fill up this space, right? Because it has no, Dijkstra does not has this idea of where it should be looking, right? So, but once it finds it, right? Of course, in this case, there's multiple solutions, right? If you're assuming this is no diagonal moves, it looks like this is no diagonal so allowed. You could do also this, right? Or you could go like this, it also would work, right? So, look at all this. Horrible. Okay, let's look at A star. Right? It's also having problems. But once it gets out, right? So, it's this wall is preventing it, right? Basically, but once it gets to this place where it can get out, right? It goes to the target, basically, right? Because again, remember, there's no, for us as humans, we look at this. Okay, yeah, you should go take this way. But I mean, how would you teach a machine that there's a wall, right? And you should go here, right? But it's actually there is a this space here, right? But there's a couple of things you could do if we assume, depending on the different problems, right? We could do it from both ways, right? Many approaches are start from the end and the goal, start some algorithm from the goal and start some algorithm from start and then meet in the middle somewhere, right? Yeah, right. So that's one of the approaches used, right? You can try, doesn't matter, breadth first or Dijkstra or even A star, but you basically start from two directions at once, right? So I think there's one here. There's swarm algorithm. I don't know what.
It's not guaranteed.
Yeah, it's swarming, but it doesn't look like. Yeah, it's not. It's gonna find something, but not too bad. In this case, it does find. Let's do the bidirectional swarm. It's gonna swarm from both ways. But in this case, it's a really bad choice because it's, no, actually it'll meet in the middle, right? It'll meet. No, it meets. Oh, and it's same cost, right? Because, right? it worked, but I don't know. I think it's about same. This part here, maybe a little bit faster than doing breadth first, like when you explore everything here, right? Or in Dijkstra, you had everything here filled out. I think this is a little less, right? Time spent. But again, that does not guarantee the shortest path. Again, if we had added weights, it could be just anything, right? So that's the thing. If you want a guarantee. Okay, but let's get back to our problem. See if we actually get anywhere. So yeah, you have your class, you have structure, but it's not complete. We would want probably you have coordinates. That's very good. That's a good approach, right? 1, 1, right? And what's your goal? You have a start 1, 1, and end is 18, 18. Again, so idea being these, of course, don't have to be. If you're not using A star or anything like that, we don't really need the two-dimensional space, right? We kind of like just any, just it could be A, B, C, D, right? These are just the identifier IDs, basically, right? So that looks good. So these are possible moves, right? So this is what you call it adjacency list, I guess. Yes, yeah, it would be adjacency list. So each node, right, knows where it go next. But we probably want the costs here, right? So we probably add the cost here too, right? Let's add the cost. Do you have a working version, or should I take a look here somewhere where we add the cost? Build a graph. In build graph, you're appending at edge, right? Graph U.
I think I submitted
You have newer version?
no, like I was just looking at the like structure that I printed out, and like at the end it seemed wrong.
Uh-huh.
And yeah, the version where it was right.
Okay, do you have a better version?
No, maybe.
How about Elizabeth? Do you have a version?
Yes, I have.
I want to see your version.
I submit my speedrun version because I read the task at bus.
Oh,
So yeah, I submit that this was actually code which I made in 10 minutes, so it's probably
very good, very good. Well, quick and dirty, right? All right, so let's take a look. All right. No. All right, Anton, let's look at your code. All right. All right, heap, okay, so you're going to do a Dijkstra, right? All right, and you have Dijkstra basically, right? And the only question, like I said, is how to parse the maze, right? So, maze append row, maze append index, and maze start goal none, you have nothing, right? So if S start row, start is row index, okay, you enumerate file, okay. Right, okay, let's take a look. Do you check it? Does it work?
it works. It gives me 90, 90, 90, or 90,
Yeah.
and the rest value. So
Okay, wait.
technically it might work, but
Might work. Let's try it one more time. Now, or start just in case. I don't want any functions messing up. Okay, so you have parsing. So what do I have to pass? You're saying it will work if. Let's go. I like the dangerous phrase. Try it. Okay, so 90. Elizabeth, do you have 90?
90.
Okay, and let's look at the path. It certainly looks decent, right? Where's my pass? Where's my pass? And come on, where's my pass? Oh, here we go, right? So we are going, 1 1. So that means 1 2, right? Probably 1 3 1 4 1 5, right? Right. And also you have nice. I love that you have explanation. Very nice. This is down.
no, it's just one extra line.
Yeah, but nice to explore the solution, right? I've had people who actually do. We had more time to do some graphical explanation, show how to color it, right? That's really cool if you could, But of course, not in 40 minutes. But yeah, it's possible to do an actual color the actual path, right? So 18, 17, 18. Right, so this shows nicely the path taken, right? So only question, right, is whether the encoding is correct, right? You have the moves, right? Directions 0 1 1 0 0 -1 -1, okay, and the cost. Let's see how do you have moves. How do you find the minimum? How do you find the priority? Return pass, right? Integer maze. If maze is digit, okay. Else 0. So what's happening here? Do you have if it's not digit, it means it's a val?
Yeah.
Yeah, it's a val. Okay. All right, makes sense. Yeah. Else nothing. But so now cost plus 0 if maze. Okay, if maze digit else 0. But okay, move explore neighbors, right? And then you push the new neighbors basically, right? Looks good. I would like to visualize this row. Let's see if we can visualize this in color. Maybe see if we can actually explore. So it certainly looks decent, right? When I print the pass, right? Where do you print the pass? Where is the printing? Okay, so Sol maze. Okay. Pass string. Okay, are you making it's a string? Oh, you join. Okay, you're joining. Okay, I got you. Okay, xy for xy in pass on the moves. Okay, that's also very good. And it'd be nice to see the costs actually, right? Can we add extra things? So in pass, find the cost. Do we have the? How do you store? Okay, let's see. How do you store? How do you read it? So you read it as what? It's a maze. It's a list, right? You append the row, and then you row. Okay, you strip the white space. Start is end from enumerate. Comes from enumerate, and row index of S, right? And row index G. And I'm trying to see how do you store. How do you store this? What's going to be? Is it going to be two-dimensional list, or let me add this something here. Let's return maze start goal, right? Maze. Let's print a maze. Maze. Okay, I'll print a maze basically, right? Print maze. Yeah, come on. Okay, it's a. For row in maze, print join. Okay, that's going to be the exact output, right? List, and this is also anything. I don't know what's going to be, right? I'll just print a row. I don't want to do joining. Let's see what happens. And then start.
I have a question.
Yes.
In your opinion, what kind of would be the best approach to do this task? In the sense, should we build a graph? Should we store in point objects? Or
Graph would probably be the most general way of doing it. Basically, like guaranteed to work, basically, right? If you just stick it in a graph and then you apply one of the well-known graph algorithms, right? Because if you can stick a problem in a graph, you have a whole selection of things to choose from. Basically, that would be the general approach. But the thing is, each problem might have some specific things which make solving this easier, right? Here, right, I believe we could use, I think A star would help here, right? Because, well, it's nudging us towards this goal, right?
well, of course, A star wouldn't be the most efficient.
Yeah.
But I meant more in the structure.
How to structure as a data, right?
Yeah.
I would say store it as a dictionary of where to go. Basically, would be classical way would be to dictionary of the coordinates, right?
Yeah.
On the where you can go, basically the possible destinations, right? Like adjacency list, right? Because this you don't have. First of all, right? If you think about it, what type of graph do you get out of this? Well, can you go from start to goal immediately? Well, no way, right? Can you go from this dot to here somewhere? No, you only have for each. It's a very sparse graph, very
Yeah.
sparse, right? So that's key. So this means if it's a sparse graph, adjacency list. So this structure, when we looked last week, right? This one here, Dijkstra, right? This part here, right? I'm talking about this, right? Adjacency list, right? So this type of structure, right? Where you can go. Because you only have 4 choices, basically, at most, right?
Yeah.
Something like this would be the most efficient, right? This type of structure, right? So, I mean, matrix, right, would be an overkill, right? Because it's going to be mostly empty, right? If you build a matrix out of this. Because the thing is, what's maybe confusing is that you have a matrix. It seems like you have a matrix already, right? But it's not really. It's not a full represent. It's not a adjacency matrix. It's just a matrix of space, basically, right? So if you build a true matrix, you have all these possible. So it will be explode in. It will be a huge graph. It will be a huge matrix with empty space, right? So that's the thing. Well, you could. The thing is, okay. So you have to think about if you stick with the default, right? If you just make a 2-dimensional list, which is 2-dimensional matrix like this, right? It's not gonna be very well. You're not gonna be. It's gonna be kind of hard to follow it. I think. I don't know. Right. So I think graph is just it's like okay, it's a safe choice basically, right? Adjacency list to be safe, guaranteed to work. But again, most efficient, maybe for some problems could be like just a regular matrix would be okay, be more.
Okay.
Yeah, so that's the thing. Yeah, so it's always a trade-off, right? If you want the most efficient, right, for the problem, or just it's gonna work, right? So I would say start with the regular graph representation and then see, if you have time and time and money and and think of something smarter basically here. Because yes, there's so this is relatively there's many ways of solving this basically as we saw. There are many approaches. You can just keep flooding basically. You could keep going basically right here, right? A flood algorithm would work here too, right? Try to flood this, right? It's like how a Photoshop or Paint program paints something, right? You could take a flood algorithm basically. Try to keep going, right? Sort of push through things, basically. That would be another approach. Which is kind of like breast first, basically, right? You keep going, basically, right? So, but that would return you just a solution, not the best solution. Here we have Dijkstra. We know it's going to be the best. All right. So, I would like to color this. So heap, priority, directions. So let's print this. Let's run this again. All right. Okay. So this is basically printed. So you set it up as a space. So the coordinates here, right? So this is 1 1, right? Yeah, that's 0 0, right? And this is what 19 19, and this is 18 18, right? All right. Okay. Yeah, that's correct. Correct indeed. Now. Can we? I would like to paint this path basically. Let's see if we can do that. You should be able to do it. We have the path, right, and we have the maze, right? All right. Make some coloring. I would like some coloring. Let's add some coloring so we can see this basically, right? We have the path, so let's color. Let's print the maze and color the path. Let's see if this. It's gonna be. I don't know. Oh, we'll see. I don't think that's gonna be. Oh, we'll see. I'll try it. That's too ambitious. I don't want to debug this really. But define plot maze. We'll see. All right. Oh my God, this will be interesting if this works. Right. Yeah, we solve it. All right. Okay. Well, this is we only did this by the way, but okay. Let's take a look. I don't know. It's gonna break horribly. No, it worked. Amazing. All right. Maybe a little some off by one errors maybe somewhere here, right? how did color it? Okay, so 0, there's a color map, 0 in cell X, right? Is this actually correct? Let's double check. Does this look okay? What are these white spots?
Probably the X's.
Yeah, I think those are X's. And this is also X, right? Yeah. I don't. Let's see. Oh, white, black. Let's do color map. Let's do different colors, right? Let's do something like, I don't know. So white is a spot. So this would be black. This would be white. Yeah, that'd be better, right? Yeah, we need color. Yeah, that's much better. That looks like actually correct. Now let's check our maze. Does this look okay? X, X, X. Yeah, this looks good. Yeah. Yeah, this is. I hate matplotlib, of course. If I had to do this by hand, I would spend probably half an hour trying to figure out the documentation for this, right? So, you know, AI saves lives and time, right? So, very nice, very nice. But again, so how does it work? Basically, right, you can see here, of course, that you're showing the cell. Basically, you know, they have color map, right? If cell is X, right, 0, right, 1, and then the add patch, right? So this is apparently the color red in these specific coordinates, right? So this is apparently the patches, right? Right, so that's kind of cool. So that is actually the path. Could we show the, of course, the numbers? It'd be nice to show the numbers actually what's taken, but that's probably too much. But I think already. But you can see the actual path taken. Compare it here, right? There's two X's, right? So it goes through here, right? Yeah, right. You can count also. We can count also the costs. Count the costs as accumulative costs, right? Count costs. Down. Nice, very nice. So let's look at this. Explore something like here. Like of course it's 0, 0, right? 6, 0, right? There's some. Yeah, 3, 4, right? You can see how it works. Say 2, 1, right? No, 2, yeah, 2, 1, 7, 6, right? And then it keeps going, yeah, up to 8. Yeah. No, it goes actually to here, right? It goes through here and here. All right. Let's see if can we add this show cost. Could we add this? I don't know if I see show actual cost of that. Oh, that's C++, right? I don't know if you can do it. Okay. Right. That looks not going to be correct, but maybe we'll see. I think that's not correct. Oh, it is? No, that's actually just numbers. Yeah, we need to get this into this I. We need to have the actual to extract the from the past, right? We're enumerating past, right? These are coordinates. We need to get get the actual costs here, right? It works actually, right? We could cost equals maze xy, I think. Let's try that one, right? That should work, right? Let's try this one more time. Yeah. Okay, now we can see what's happening, right? That's better. Right, so 0, we go down, 3, 4, 4, 4, 1. Yeah, right. You can see, of course, how Dijkstra optimizes for the you know, the cheap costs. So 0, 8, right? It knows where to go down. All these extra 0, these cheap flights or cheap you know, where there are no monsters, right? It takes those paths and optimizes for 3, 4, right? Pretty nice, actually. Right. So again, so from what's takeaway from this lecture, from this the lesson is, of course, is to the hardest part is converting to the graph, right? The correct structure, right? Then you have a wide variety of algorithms to apply, right? You only right now know Dijkstra. You'll learn about A star or some other ones, right? And You can solve many problems actually. You know, maze is the obvious, but many things actually transfer to these type of representations, right? You can think of, you know, if you have some sort of costs and you have some connections, that's a graph there basically, right? So, and you can apply it then. So it's the only question is how to figure out how to, you know, how to represent this problem as a graph. Here it was relatively easy. Any questions? I will submit this so you can check this solution. So very good, Anton, on the solution, right? So what was your? Do you do a prompt or how do you do it?
I only like do a prompt for output because I'm actually was lazy to write
Yeah.
it by hands.
But you were able to. Did you do this on a bus on your laptop?
On the bus, I just mostly just like read the task, and the idea was actually mostly I think about it when I came here and
Yeah.
just write.
Yeah.
And yeah,
Yeah,
debugging
yeah,
some
yeah.
because my Python doesn't work. Probably.
Yeah, it worked. Very good, guys. So everyone who submitted, right? So submit if you have something sort of working, right? So do you guys good? You submitted something. Very good. All right. So we'll start 11:15, and we'll see what we do about C++.